My name is Philip Brokum, and I'm going to introduce you to differential equations. The best part is, you don't have to know any calculus in order to follow along. I like to think of them as difference equations. We are going to use the example of a car traveling down a road. The x-axis will represent the position of the car. Here we are at the 3-mile marker after 10 minutes. 5 minutes later, we are at the 7-mile marker. The change in position, dx, or the difference in x, is 4 miles. The change in time, dt, or the difference in t, is 5 minutes. dx dt is 4/5. Don't forget that this actually stands for something. It literally means that we are traveling 4 miles per 5 minutes. It's a speed. It's an unusual speed though, so it makes sense to multiply it by 12, which gives us 48 miles per 60 minutes, or 48 miles per hour. This is the velocity of the car. Velocity is the first derivative of position. It is written as x dot or dx dt. Acceleration is a bit more complicated. Here we are at the 3-mile marker after 10 minutes, at the 7-mile marker after 15 minutes, and at the 15-mile marker after 20 minutes. The average velocity of the initial leg of our journey, the orange arrow, is 48 miles per hour, as we just calculated. The average velocity of the second leg of our journey, the green arrow, is 96 miles per hour. I know this because in the first leg we went 4 miles in 5 minutes, and in the second leg we went 8 miles in 5 minutes, so we're going twice as fast. The change in velocity, dv, or the difference in v, is 96 minus 48, which is 48 miles per hour. That means we accelerated 48 miles per hour since the first leg of the journey. This does not mean that our acceleration is 48 miles per hour. You cannot accelerate at 48 miles per hour. You need an extra unit of time. It's very confusing, so I'm going to try to explain it with a more familiar concept. Gravity. The acceleration of gravity is 9.8 meters per second squared. What does the squared mean? It means that the acceleration of gravity is 9.8 meters per second. Mathematicians just like to write the two s's as s squared. Pretend I'm dropping a ball. At time 0, the instant I let go, the velocity of the ball is 0. It hasn't started falling yet. 1 second later, the velocity of the ball is 9.8 meters per second down. Why? Because gravity adds 9.8 meters per second. It's been 1 second, so it's falling at 9.8 meters per second. At time 2, after another second, we are going an additional 9.8 meters per second down, for a total of 19.6 meters per second down. And at time 3, we add yet again another 9.8 meters per second, so our total velocity is now 29.4 meters per second. This is why, when you drop things, they start falling faster and faster and faster. Acceleration is the second derivative of position. It is written as x double dot or d squared x dt squared. D squared x dt squared? Where did that come from? I will briefly explain where this notation comes from. D over dt is the change over time. dx dt is the change in x over time. If we replace the x with the expression itself, dx dt, the velocity, we get the change over time of the change over time of the position. There are two derivatives there. This is why it's called the second derivative. Again, it is the change in time of the change in time of the position, or the change in time of the velocity. If we rewrite this horizontally, we get d over dt times dx over dt. Remove the parentheses, regroup, and we have d times d over dt times dt, which becomes d squared x over dt squared. Going back to our acceleration example, if the acceleration is not 48 miles per hour, what is it? Well, the acceleration is 48 miles per hour per something. We can't actually figure out what the acceleration is, and it almost doesn't make sense. When you're driving down the road, you probably aren't going the same speed all the time, and you probably aren't accelerating the same way all the time. You're probably weaving in and out of traffic, you're probably hitting the brakes, you're hitting the gas. So to say that there's an exact number for the acceleration might not make sense. But more importantly, from a mathematical perspective, is that differential equations such as these are often difficult or impossible to solve without something we call initial conditions. These are assumptions or measurements made at the beginning of an experiment that are necessary in order to answer the question. So in our example, we're going to make it simpler by removing the middle dot and just going from A to B. One initial condition is going to be that our velocity at time 10 when we start is 0 miles per hour. We are going to start standing still at the 3-mile marker. Another initial condition is that our acceleration is constant. We are not hitting the gas or hitting the brakes. We're going to be nicely, steadily accelerating at a constant rate. The question then is, what is our final velocity at time 20? How fast are we going when we hit the 15-mile marker? One thing we know is that the total distance we have gone is 15 minus 3, which is 12 miles. The total time we spent is 20 minus 10, which is 10 minutes. And the average velocity of our entire trip is 12 divided by 10, or 1.2 miles per minute. Multiply that by 60, and we get 72 miles per hour. Now, if we know the beginning velocity, 0, and we know the average velocity, 72, can we find the end velocity? Yes, we can. The end velocity must be 144 miles per hour, because 144 and 0 average out to be 72. If you don't believe me, look at this graph. This is a graph of constant acceleration between the 3 and the 15-mile markers. We start at 0 velocity, we end at 144 velocity, and you can see that the average velocity is 72. If you remember, any 2 points will uniquely define the line. So if we know 2 points, and we do, we can find the third. One point we know is that we start at 0 velocity. Another point we know is that the average is 72. We can then extrapolate and figure out that the final velocity must be 144. So the answer to our problem is that the final velocity after 20 minutes is 144 miles per hour. Let's go back to our initial conditions example, and we even have one more. I guess you would call this a final condition. We know that the end velocity at time 20 is 144 miles per hour. So let's ask another question. What is the acceleration in miles per hour per hour? Now remember, one of our initial conditions is that the acceleration is constant. So we will be able to get an exact number for this acceleration. We were unable to do that before because, as I was mentioning, the acceleration would probably be changing as you drive along and move between lanes. Now we're assuming the acceleration is constant and we can actually figure it out. Velocity equals acceleration times time. Why? Well, imagine you're accelerating at 5 miles per hour per hour. After 10 hours, you're going 50 miles an hour. So this is the equation. Velocity equals acceleration times time. We know the velocity. It's 144 miles per hour. We also know the time that it took, 10 minutes, because we went from t equals 10 to t equals 20. So 144 equals 10a. Divide by 10, and we get 14.4 equals a. Answers aren't that useful without units. What does the 14.4 mean? Well, velocity is in miles per hour, and time is in minutes, so our units are 14.4 miles per hour per minute is the acceleration. That means that every minute you drive along, you're going 14.4 miles per hour faster than you were 1 minute ago. Let's multiply this by 60, and the acceleration is 864 miles per hour per hour. That is our final answer. Anyway, I hope you enjoyed this video, and I hope you walk away with at least a rudimentary understanding of what differential equations are and what they're used for. Feel free to watch my other videos on YouTube.